Welcome back. We in the previous class we concluded our discussion on photolithography, and now we move on to some of the recently development alternative lithography techniques, which are much simpler, much easy to execute, which are often specific to the polymers and other classes of materials, and most importantly they are cheap, easy to implement, low cost, and are not specific or not or beyond the scope of microelectronic industry. And we start our discussion with one such method, which is nano imprint lithography. Before that, we just want to have a quick look. I mean, though we talked about photolithography, it is very difficult to sort of find out any other technique which has as much potential or as much importance as photolithography in particularly in the microelectronic industry. There are several limitations of photolithography. For example, it requires extensive instrumentation and facilities with high capital investment. You can understand based on the discussion we have had that really it requires a whole lot of infrastructure, mask aligner, stepper, UV exposure, fabrication of the mask, then a whole lot of development sequences, spin coating, etc., etc. The pattern resolution, this we talked in one of our earlier lectures, the pattern resolution is limited by the optical diffraction. So, depending on the wavelength of light, you cannot really go below a certain critical lateral resolution irrespective of whatever is the feature size on your mask. The method is not suitable for patterning of all type of polymers. This I guess you understand by now. You need a photoresist or a photosensitive polymer to pattern by photolithography, or in other words a photolithography can only directly pattern a photoresist film or a film or a layer of polymer which is photoactive, but there are a whole lot of polymers which do not have significant optical properties, and therefore photolithography cannot be used directly to pattern those type of polymers, which is a major, which might be perfectly fine from the standpoint of microelectronic industry, but as we have talked in one of our initial lectures where we talked about a whole lot of application of patterned polymer surfaces, you may want to create structures with other types of polymers other than photoresist, because do not forget photoresist again is extremely expensive compared to other general polymers, thermoplastics or elastomers, let us say. So, photolithography directly you can't apply for patterning other types of most other types of polymers. The technique requires harsh processing conditions, such as the technique of photolithography requires harsh processing conditions such as exposure to UV radiation, chemical etching, etc., and therefore has limited application for sensitive materials, particularly if you are working with biological samples or living cells, because now there has been lot of work which involves patterning of molecular living cells, proteins, etc., etc. And so, since you have UV radiation and lot of dissolution in solvent and things like that, you just can't use photolithography for those type of sensitive settings. And another major thing which we never talked when we were discussing photolithography is that the method cannot be easily applied, or the method cannot be adopted for patterning a film coated on a non-planar or a curved surface. So, everything was sort of taken for granted that your film has to be on a flat surface, you place a mask which is parallel to that, you do an exposure, etc., etc. But there are settings, there are cases where you want to create or pattern a surface or a film which is not coated on a planar surface. Okay. So, these are some of the severe limitations, some of the limitations of photolithography, but still for the microelectronic industry photolithography is the best possible bet, and research is significantly on in that area. But in one of our previous lecture we also talked about Moore's law, and the projections that Moore's law make, there is severe doubt that because of this diffraction limitation whether one can really achieve structures much smaller, I mean smaller than 10 nanometer or at a nanometer level by photolithography, to where the microelectronic industry or the feature size or the transistor size or the line width is eventually poised to head. So, there is a significant search for other techniques which can sort of complement photolithography even in microelectronic industry, and some of these techniques which we are going to talk subsequently. One of them what we get started today is what is known as the nano imprint lithography. and a whole lot of soft lithography methods what we discussed in one of the subsequent lectures are sort of potential candidates for even replacing photolithography in may not be that close near, but maybe in distant future. Of course, the genesis of both of these set of techniques was not to complement photolithography, but to work out as a low cost, easy to implement alternative for patterning various classes of polymers and other types of materials also. So, both the imprint group of techniques, the nano imprint group of techniques, which often also go by the name hot embossing, as well as soft lithography, they are now capable of patterning not only polymers, but other types of materials like inorganic sol gel films or even metallic thin films under certain conditions, and we will see in some of our subsequent lectures about some of these developments. So, we get started with nano imprint lithography in this particular class, a technique that was developed in the middle of 90s. So, these are pretty recent developments. I mean, this entire area of nano imprint lithography and soft lithography is at best some 14 to 15 years old. Still a lot of research is going on, and the potential was so high. I mean, the area is so significant that you have not less than at least 20 publications in the last 15 years in the top scientific journals of nature and science on these particular themes. These group of techniques were pioneered by two great scientists, Stephen Chow at Princeton, who pioneered the concept of nano imprint lithography, and George Whitesides at Harvard, who came up with his amazing concept of soft lithography. In the next 2 or 3 classes, we will be discussing in details about some of these techniques, and I am sure as compared to photolithography, once you listen to these methods, you will find that how amazingly simple these methods are, and even in a high school laboratory you can sort of implement some of these techniques with ease. So, we will I will try to give you some examples, hands on examples, which all of you can actually try out to do. Okay. So, the concept of nano imprint lithography is very simple. This schematic gives you an idea. All you take is a mold or a stamp. So, it is like a rigid, it can be on silicon, it can be on silicon oxide, it can be a photoresist, patterned photoresist layer made by photolithography. You take a stamp, often referred to as mold in nano imprint lithography. Stamp is more of an word which is more frequently used in soft lithography. Soft lithography is something we are going to take up in the next class. So, just keep it in mind. The mold is in some way equivalent to the mask of photolithography. Okay. Now, photolithographic mask of course contains the more of a 2D structure of the desired pattern you want to make. In contrast to that, a nano imprint lithography mold or a stamp actually contains a physical relief structure. So, you have these structures, this is the mold. What you do, you take a polymer film, on a rigid substrate. This substrate can be silicon, but since many of the nano imprint lithography made structures might find application in non microelectronic settings. So, there is it is not at all mandatory that you have to work with silicon. It can be glass, it can be quartz, or it can be other polymeric surfaces also. Of course, there are various similarities or various techniques which were sort of developed for photolithography also find application here. For example, when you want to make this polymer film, what is the best bet or what is the best way by which you can make it. Well, spin coating still finds extensive application here. We have discussed in details about spin coating in the context of photolithography, but one can also work with something like dip coating, drop casting, or whatever method you want to really use, really does not matter. So, easiest example or the classic NILs work with thermoplastic polymers. Without going too much into the details of the chemistry of these materials, all you should know that these are polymers which are solid like at room temperature, and they if they are heated up, they sort of soften. And there is something I think we have talked in one of our previous lectures called the glass transition temperature, above which they become significantly soft. Okay. In other words, you might be knowing that polymer is an amorphous material. So, at room temperature most thermoplastics have very high viscosity, to simply put it. The viscosity is sort of so high, so it is more like a frozen in liquid. And the viscosity you might have learned from your fluid mechanics course, it sort of is an indicator of resistance of a liquid towards any sort of deformation or any externally applied force. So, higher is the viscosity, slower will be the dynamics subjected to the same force as compared to a liquid which has lower viscosity. So, for this type of a thermoplastic at room temperature, what happens is the viscosity is so high that it virtually behaves as a solid. Now, when you heat it up beyond its close to its glass transition temperature or to temperatures above its glass transition temperature, what happens is it becomes soft. That is, there is a significant reduction in viscosity. Complex fluid, there are a lot of concepts, how it happens, how the entanglement changes, etc., etc. I am skipping all the details. All you need to understand that you take a thermoplastic, most of the plastic, even this pen for example, if you put it on a hot plate, it will melt, you know that. So, the body is made of a plastic, it is a thermoplastic material. So, at room temperature this is behaving just like a solid, and you sort of heat it up, it sort of becomes soft. Okay. So, this is a very simple concept we need to know. If any one of you is interested, you are free to search the internet for with keywords like glass transition temperature, thermoplastic, you can look at the chemical compositional details and things like that. But for the context of this particular course, I will be skipping all those details which I do not feel is that necessary. So, understanding this much, that a thermoplastic behaves like more like a solid film at room temperature, and then once you heat it up beyond its glass transition temperature, it softens or behaves like a lower viscosity liquid, you can probably now understand how nano imprint lithography works. It is very simple. So, this is the hardware requirement, as I have already told, that you take a topographically patterned rigid stamp. You take a polymer film on a substrate. So, at room temperature this film is more like a solid. All you do is heat up the film. Okay. So, once it heated up, this sort of goes to a molten liquid state. Once it is in the liquid state, you bring in this stamp and press it hard against the film. So, here is the stamp, here was the film, now it is heated, you apply an external pressure. So, since this is now simple. So, since you are pressing a structured mold against a liquefied and molten film, the liquid will try to sort of follow the contours of the patterned mold, and all you do is after reaching this stage where a perfect negative replica of the stamp pattern has formed on the liquid film, you just cool it down. So, as you cool it down, what happens is that the liquid again goes back to its frozen in state with higher viscosity, but now since the stamp is still there, the frozen in liquid does not have a flat top surface, but it replicates a negative replica of the mold pattern on its surface. So, in the process you have created a patterned polymer film. Okay. So, after the cooling is done, all you have to do, you have to withdraw the mold. Okay. So, if you now compare it with the patterning of a photoresist layer or creating of a patterned photoresist layer, which was in photolithography, which was again a polymer, you see how simply you have done it. There you required a mask, you required an UV exposure, you required a baking, development, etc., etc. But here what you do, you just take, so step 1, you take a polymer film, you take a rigid topographically structured stamp or a mold. I would be more careful in using the word mold, which is more specific to the nano imprint lithography group of method. Second stage, you heat up the film, bring the mold in proximity to the film, press it hard against the mold, cool the whole assembly while the mold is in place. So, that sort of makes it takes the liquid back to the frozen in state, and then simply remove the photoresist layer, the mold. So, you have a structured polymer film. The structure replicates a negative replica of the original mold pattern. Of course, if you are talking about an microelectronic application and sort of let us say this is again back to silicon or silicon oxide. So, you want to have access to the substrate, because this way embossing does not guarantee that you are going to have a structure like this. This is not guaranteed. Okay. So, chances are that you will have even below the valleys on the structured film, you will have a remnant polymer layer. And if you really if you want to sort of look at hydrophobicity or something like that, or want to do some experiments with structural color, you are perfectly happy with this type of a structure. So, this actually is good in many settings, because the upper part of the stripes as well as the bottom part of the valley have the same material. But if you are sort of interested in having access to the substrate, of course, you want to preferentially remove the polymer over these areas, and by the method of what is known as RIE, reactive ion etching. So, you see, if you now compare with photolithography, what we have, I am repeat time and again comparing with photolithography, because that is something which you already know and we have discussed in somewhat detail. If you compare with photolithography, in conjugation with nano imprint lithography and reactive ion etching, you can go to the same stage, and subsequently what follows is etching. If you have, this is the oxide layer, you can do the etching and you can have direct access to the silicon surface and follow it up. I mean, then it becomes very similar to the later processing stages of photolithography itself. So, in principle, a nano imprint lithography group of techniques also has the potential to be used in the fabrication of microelectronic components, but its scope sort of extends much beyond that, and for bulk nano application as well as rapid prototyping, nano imprint lithography is one of the easiest methods to implement. I mean, I am sure we actually have already discussed the basic principle of nano imprint lithography. So, you can imagine that understanding the different stages of photolithography took us some 4 lectures, but here it takes roughly 10 minutes to understand. It is so simple. So, in principle, you take a rigid patterned stamp and or a mold, and you just press it against a softened polymer layer, freeze the structure right there, take out the stamp. I mean, you have the negative replica of of the desired pattern on the polymer film. Now, we Indians are all big time fans of sweets, and if you walk into any sweet shop in my part of the country, that is Bengal, or in North India, or in all other parts of the country, you find beautifully decorated sweets. Sandesh, they come with nice designs. So, what exactly are you doing? You have some sort of a mold to which you are pressing the chena, and then you are just creating a nice looking sweet, or with a desired structure. So, people might laugh, but that is exactly what you are doing here in nano imprint lithography. It is so simple. Of course, there are some nitty-gritty issues which we will now discuss, but conceptually this is what nano imprint lithography or hot embossing refers to. Why hot? Because in the classical form, or in most nano imprint lithography settings, you actually start off with a homopolymer film, and then you gradually heat it up beyond its glass transition temperature, so that it's softened, and then you do the imprinting at that stage, which has its advantage, because you are sort of embossing a softened layer. So, you need much less forces, but there are some associated disadvantages also, which we will discuss in the subsequent few minutes. So, now I guess this picture makes perfect sense to you. So, you have a pattern mold, you have a resist or a polymer layer, you have a substrate, you heat it up, press the mold against it, you get the negative, then cool it down, get a negative replica of the pattern, and if you want to have direct access to the substrate, you apply reactive ion etching subsequent to nano imprint lithography. This sort of cartoon on the right hand side will also give you a clear idea. So, here at the starting hardware you have a master pattern or the mold which has the topographic relief structures. You have a surface to be patterned, a polymer film on a rigid surface, let us say. And so, first you start off with by heating the film. So, that film heating is typically it is heated to temperatures beyond the glass transition temperature. So, once it is heated, you sort of the polymer film becomes soft, and then you bring in the mold or the stamp, press it hard against the heated polymer film with the application of external force, and then you cool it down while the external force is still being applied and the stamp or external force the stamp is pressed against the polymer layer with the application of external force. Cool it down so that the polymer goes back to its frozen in liquid state, and then at this stage you would like to remove the stamp. So, the pattern freezes and you remove the stamp and you get a negative replica of the stamp pattern on the film surface. So, I will quickly go through the cartoon sequence again. See, now you will understand every step. So, you have a mold or a patterned stamp, you have a polymer film. You first start off with heating up the film to a temperature beyond its glass transition temperature, so that the film becomes soft. Now, you bring in your stamp or the mold, press it hard by the application of an external force. Now, once the pattern transfer has occurred, you cool it down, the patterns freeze, and then you detach the original mold. So, this is in a nutshell the process of nano imprint lithography. It is very, very simple, rather easy to execute. So, here is some sort of classical definition. Nano imprint lithography, which is commonly referred to as NIL, that is the standard acronym for nano imprint lithography in the lithography community, developed by Chow and others. As I told you, Professor Chow is at the University of Princeton, is also called hot embossing, and usually uses a hard rigid master or a mold to physically deform a solid polymer film that is on a rigid substrate. Okay. The polymer on the substrate is typically heated above its glass transition temperature, and the master or the mold is pressed against it. The polymer is deformed, filling the voids in the master. So, essentially these are the voids, you can say, in the master, which the once you bring it in contact, the polymer fills up. Okay. So, the polymer deformed, filling the voids in the master, then it is cooled to below Tg, and the master or the mold is removed, revealing a pattern that is inverse of the master or a perfect negative replica of the master. You read the sentences or whatever is here carefully, and you can correlate it with the sequence of events that is shown here. You see that in the classical sequence or the definition of nano imprint lithography, there is no mention about reactive ion etching, because of the fact that nano imprint lithography as a process does not require this RIE. Nano imprint lithography will lead you up to the stage 2 on the figure shown in the left hand side. If you require access to the substrate, you additionally would like to apply reactive ion etching. So, in principle it is something very, very simple. You take a thermoplastic layer, you heat it up beyond its glass transition temperature so that it becomes soft. You have a mold or a master which you bring in, press, and the liquid polymer fills up. These are referred to as the voids or the valleys on the stamp or the mold surface, and you get to a negative replica of the stamp pattern on the film surface. Now, this is in the nano imprint lithography in the most classical form, but there are quite a few techniques which have sort of been developed or derived from the classical nano imprint lithography after its invention by Stephen Chow in 1995, which sort of addresses some of the critical issues or problems of NIL in some form or the other. The major derivatives or major extensions of nano imprint lithography is UV nano imprint lithography or UV NIL, solvent vapor assisted nano imprint lithography, room temperature imprint lithography, and this is a pioneering work that was developed by Hong Lee's group in Korea and did not come from Stephen Chow's lab, rapid flash patterning, laser assisted direct imprinting LADI, this is again 2002 work by Stephen Chow's group, where this technique NIL was extended to beyond polymers, and it was shown for the first time that nano imprint lithography can be used directly to pattern a silicon. So, finally, you want your structures on silicon oxide or silicon, but LADI it is again a pioneering path breaking work, was one of the first techniques where it was shown that nano imprint lithography can be straight away used to pattern silicon. And then the one of the later developments is the roller nano imprint lithography, which sort of tries to make this nano imprint lithography based techniques or imprinting based techniques into the continuous mode. Because if you look carefully, the very concept of imprinting, you take a pattern substrate, you take a film, you bring it under the stamp, you heat it up, you then press the stamp, cool it down, and then withdraw the stamp or the mold, and you withdraw the film also, is conceptually a batch process. Now, this roller nano imprint lithography sort of allows it or aims at making NIL group of techniques into the continuous mode or a more of a roll to roll process. This is becoming extremely popular as a in flexible electronic industry. So, we will discuss some of these techniques in somewhat detail. So, this is again a quick look at the classical nano imprint lithography, which was originally published in this form in 1996, exactly 15 years before. So, polymethyl methacrylate was the polymer that was used for that particular experiment. One of the critical thing of a proper NIL resist instead of photoresist, if we are allowed to use or refer to this polymer film as an NIL resist layer, is one of the critical requirements, since it involves a thermal cycling, is that it should possess a low coefficient of thermal expansion, which is pretty low for PMMA. The pressure shrinkage coefficient, another very critical parameter, because ultimately you are going to apply, when you are embossing, you are going to apply a high external pressure. So, if there is a significant pressure shrinkage within the polymer due to voids present in the within the structure or within the matrix, it is also detrimental for the whole process. So, you do not really want to have a very high pressure shrinkage, and so essentially PMMA was picked up for both these nice compatible properties to NIL, a very low coefficient of thermal expansion and a low pressure shrinkage coefficient. Typical temperatures vary from 150 degree to let us say 200 degree centigrade, depending on the molecular weight. The glass transition temperature of PMMA is around 115 to 125 degree centigrade. With the back of the envelope, you may remember that we are talking about polymers. So, though so PMMA, simply stating PMMA is only part of the story, the other important parameter is the molecular weight. So, higher molecular weight essentially would refer to longer chain molecules, which anyway will be more difficult to dislodge, and so higher chain molecules or higher molecular weight polymers typically tend to have higher viscosities, which is reflected in terms of a higher glass transition temperature. But irrespective of the precise molecular weight, the glass transition temperature may vary by 15-20 degree centigrade. It can vary more. I mean, for very low molecular weight thermoplastics, it can sort of be liquid even at room temperature. But if we are talking about some standard molecular weights like some 1000 kilodalton and above, right up to about a million, it will sort of have a glass transition temperature somewhere around 115 to 125 degree centigrade for PMMA. So, this is the temperature that was used for embossing. Pressure was kept at around 30 to 50 millipascal. Biggest advantage of embossing from the standpoint of lateral resolution of feature is that you ultimately create a negative replica of your stamp pattern, and your diffraction, optical diffraction, or the wavelength of the light source you were using for your exposure, as in case of photolithography, does not have any influence here or any role here. So, what we talked in terms of as one of the major disadvantages of photolithography is that the lateral feature size is diffraction limited, is in no way responsible in case of nano imprint lithography or embossing based techniques. So, if you have the right stamp, then it is possible that you can create as small a feature size you want to create. It becomes a difficult, it becomes another question, of course, how does one create the original stamp? I mean, that is something I am going to talk maybe in, I mean, this is a common problem or a common question for both nano imprint lithography or embossing based techniques as well as soft lithography based techniques, that though these techniques are very easy to implement, you just heat up a polymer layer, you just press the stamp or the mold and you get a negative replica. One question you might think is how does one originally create the stamp, and in many cases the first stamp has to be created by either photolithography or by some higher end other next generation lithography techniques like electron beam lithography or focused ion beam lithography or something like that, which makes the stamp a very costly and an expensive commodity. But once the advantage is that once you have a stamp, you can use it several number of times to create go on creating structures. Even from the from the beginning, it was realized, the beginning of the invention or beginning when the technique sort of came into existence, that there is no diffraction limitation, and the lateral resolution of the feature size was entirely governed by the availability of the right type of the stamp. So, way back in 1998 itself, 25 nanometer lines were produced. Photolethographically, technology was stuck at around 250 nanometers at that point of time. So, it was a huge quantum change in lateral resolution of patterned features. As late as 2004, 5 nanometer lines have been successfully produced by nano imprint lithography. But of course, you need to realize that if you are creating 5 nanometer lines, you actually need to have stamps or molds which itself has a very low lateral dimension. So, this is really very important as to get the, or to a large extent, the success of NIL based techniques. Depend on the availability of the right stamp. Well, we do not intend to really cover in greater detail about the higher end lithography methods for stamp making. Maybe we will just quickly glance through some of the names like E-beam writing or focused ion beam, etc. But we will it is an important thing to remember that your feature size, the lateral resolution of feature size has no limitation due to diffraction or any other optical property, and entirely depends on the availability of the right type of the stamp. The one of the steps, I mean, if you look at the standard NIL, one of the first things that you need to do is that you need to heat up your polymer. So, you have a thermal cycle associated with the step, and for that you have to pick up a material which shows a low coefficient of thermal expansion. So, idea is that you take a polymer which is solid at room temperature, you take it to the liquid phase where you want to emboss and achieve your pattern transfer, but at that stage you sort of in order to achieve to that stage you need to heat up the polymer. So, once you heat up, the coefficient of thermal expansion becomes an issue, and therefore, it becomes difficult to handle polymers which do not have a low coefficient of thermal expansion. So, one possible remedy of this was suggested was the nano imprint lithography using a UV curable resist, which is often referred to as the step and flash imprint lithography. So, it is pretty similar to the conventional NIL, but the only difference is that you do not take a polymer layer, but you typically do not take a thermoplastic at room temperature, but you sort of use a UV curable resist which is liquid at room temperature, and of course, your mask or the stamp or the mold has to be UV transparent. So, all you do that instead of coating a film which is solid at room temperature, you dispense a liquid in the liquid state at room temperature. So, it remains in the liquid state at room temperature, but the only additional property you need to ensure that this liquid is UV curable. So, again you are partly back to the regime of photolithography to some extent, that you are like a photoresist, you are actually relying on a polymer or a material which is photosensitive. So, it is liquid at room temperature, but it is UV curable. So, since it is liquid at room temperature, what you do, you just bring in the stamp and emboss it against the liquid at room temperature. So, since you apply a pressure just the way you have done in case of the classical NIL, but your thermal cycling is not at all necessary here. So, your heating stage is gone. The advantage is that the chances of a thermal coefficient mismatch and a volume contraction or volume expansion due to the thermal cycling is also gone now, and all you do, instead of after the imprinting is over, the liquid has filled up the voids, all this thing has happened. Unlike cooling, what you typically do in conventional NIL, you just do an UV exposure, and by UV exposure what happens is there is chemical modification or chemical polymerization that goes in this polymer within this polymer, or in other words if you do an UV exposure, there is physical cross linking within the polymer and the patterns become permanent and sort of it freezes, and once the pattern freezes due to cross linking engendered by UV exposure, you simply lift off the stamp. So, advantage here, I mean, so avoids the heating stage, the pressure required is also reasonably low because typically it is at a liquid state. So, it is at much more low viscosity as compared to a molten polymer. A quick look at the differences between the thermal NIL and UV NIL. Of course, UV NIL has its own advantages, but has its own limitations also, as you can see, because the biggest advantage, one of the major advantage we talked about initially about nano imprint lithography is that it is not material specific. That advantage is lost in UV NIL because you are again talking about a material which is UV sensitive. I mean, you can't really work with any polymer. So, let us have a quick look as what are the differences. So, thermal NIL, it's there is less restriction on the template, or you can have any material, pretty much all the conventional materials like silicon and nickel on the template or the mold or the stamp. In contrast, in UV NIL you have to have a mold or a stamp which is the stamp or the mold has to be transparent to UV. Okay. So, there is a severe restriction in UV NIL severe restriction from the standpoint of materials, not only so material here includes the resist, as well as the mold or the stamp material. So, this is critical. The resist or the liquid has to be, it has to obey two properties. It has to be a liquid at room temperature, and secondly it has to be UV cross linkable. Okay. In contrast, the mold or the stamp has to obey property like it has to be UV transparent. In contrast, in thermal nano imprint lithography, far less material restriction. You can have a stamp or a mold of any material, it can be silicon, it can be nickel. Here, since it has to be UV transparent, it almost automatically implies that you need to have a quartz or silica stamp which is UV transparent. Also the NIL resist, no optical property required. And since you do not need a liquid, so you can have different molecular weights also. But in contrast, it does require that you have a low CT and low coefficient of pressure pressure shrinkage material. Thermal NIL is in a way a slightly simpler, or as some people mention it to be cleaner process. UV resists, since they are liquid at room temperature, have a tendency to be more viscous and are often difficult to handle. So, if you really have a more viscous resist, one of the major problems is during the process of creating the film by spin coating itself. So, if you have a high viscosity liquid, there is chance that your initial film thickness will not be very smooth. And of course, exactly I remember we have talked about the existence of an yellow room in the context of photolithography. So, the moment you are actually working with a UV curable resist, it also implies that it is necessary that you need to take all the precaution, because you do not really want your liquid resist to sort of start cross linking or hardening during the processing step itself. Of course, thermal NIL more readily available polymers or resist, because you can work with pretty much any type of polymer. Almost all thermoplastics can be handled by thermal NIL. Advantage of UV NIL, of course, there is no thermal cycling. So, you sort of save on the hardware, you save on the critical issues of heating, controlling the temperature, then cooling it down and then detaching. So, it is a far less step intensive, I would say. Any possibility of thermal coefficient mismatch issue does not remain at all. So, there is no possibility of coefficient of thermal expansion mismatch. It is much faster. It requires just a couple of seconds or a few seconds, because of the fact that you have a the UV curable resist layer or the UV curable polymer layer, which itself is in the liquid state. Here you, after coating the film, so it has to be heated, then embossed, then cooled, then stamp or mold removal. So, it has quite a few. So, these are the sub steps of the thermal cycle, and it of course requires time. In contrast, it is already in the liquid state. So, straight away emboss it, do the UV exposure, your patterns have already formed, just remove the stamp. Okay. So, that way it is much faster, much faster. But it, of course, we have talked already, it requires has its own problems with material issues and things like that. Of course, since you do not have the thermal cycle, so coefficient of thermal expansion and its mismatch between the polymer and if there is an expansion of the mold or the stamp material. This is what we are talking about, the CTE mismatch. That question does not arise. So, that is another major advantage. Of course, if you have a polymer which might degrade if it is heated to a higher temperature, again that is a major problem in the conventional thermal NIL, which can be addressed by UV NIL. As far as working with living cells is concerned, I would suggest both the techniques are pretty much equally bad, because in one you are exposing your living cells to high temperature, in the other you are exposing your living cell to a harsh processing condition in the form of UV exposure. So, it is not good for any one of them. Some of the soft lithography techniques which really does not have a thermal cycling as well as does not require an UV exposure are much better suited for biological applications. In thermal NIL, coming back to the comparison, thermal NIL of course requires pretty high temperature, and temperatures can be as high as 200 degrees centigrade. Well, there is a possibility of coefficient of thermal expansion mismatch between wafer and the stamp, and requires a larger force as compared to much lower forces which are necessary in UV nano imprint lithography, and much higher forces may result in distortion of the alignment and also possible breakage of the substrate as well as a stamp. That is a real problem in nano imprint lithography, and you understand by now that a stamp is a really costly piece of hardware. So, if there is a breakage, it is going to sort of pinch you hard, getting a replacement stamp and things like that. In contrast, of course, UV NIL has these advantages, but volume shrinkage, there is significant volume shrinkage. This is important. In UV NIL, there is significant volume shrinkage due to phase transition. This phase transition occurs when you are exposing the patterned resist layer after it has been imprinted or embossed with the stamp, UV exposing it. So, there might be significant volume shrinkage. As we have already told, because you are working with high viscosity UV curable resist, it might be difficult to obtain uniform layers from spin coating, and of course, there are a lot of material restriction on UV stamp. So, this is we have talked in this class about some of the basics of nano imprint lithography and two of the most conventional form or most popular forms of nano imprint lithography, that is the thermal NIL and UV NIL. In this next class, we will pick up the discussion from here and talk about the other variants or modes of nano imprint lithography.